All right. Is everyone in the meeting, by the way? Okay, I can see all of you. All of you, you are there. Okay. So in this session now, we'll be talking about the conformation of cycloalkanes. Remember, we just talked about alkanes and cycloalkanes in the previous session. All right. So in this video, I'll continue saying it tackles pure chemistry. Those guys who are in pure chemistry, I'm sure you can see yourself. That is there on your portal 260, right? Pure biology, we will also have this course, so you know what I'm talking about. So we'll talk about staggered eclipse, sigma bonds, everything like that. What is conformation? So let's get started. Okay, so what we need to know, first of all, when you see, let's say I give you this compound, all right? So I give you this compound or this molecule. So this molecule you can see is what we call now is an organic chemist, which is falling under the family of alkane, and the name shall be named as what? As ethane. All right. So this is what? Ethane. Okay. So we know this as ethane. Then what we need to know is that there is what we call pi bond and sigma bond. But for a sigma bond, is a frontal overlapping of orbitals. Let's say I have C and C there. So this is what? This is the sigma bond. All right. We talked about this in the previous session. So this is a sigma bond. It occur through what? Front to front of these guys involved in the bond. So that is it. But in a situation whereby we have pi bond like that, this doesn't happen to say the bond will be frontal, like two loops connecting the front thing. No, this one happens like if you have two pi's. So I mean, if you have a pi bond, so the first one which will happen at the front, which is called front overlapping, it is what we call now a sigma bond. Then in this side, all right, this side, there's what we call now a pi bond, which is just happening. This is a sideway overlapping of orbitals. So the orbitals will overlap like that and also form a bond here. All right, so they'll form a bond here. There they form a bond. That's the reason when we have a what, and the bond that is formed there, that's what we call pi. So in a situation whereby you have three of them, all right, three of them, the Leo analysis or the Leo bonding happen like in the front, like front to front, it's one bond which is sigma. Then the other one, the other bond now will happen like this. The other bonds will happen like this. So these are the bonds now. This is another pi and this is another pi. They are more like waves. They are not really actual. They are not that strong, okay, as compared to what? To sigma bond. So this is what we call now pi bond. All right, and also pi bond. That's the reason why in triple bond we have two pi bonds. All right, and one sigma bond. All right, so sigma shall be presented by that. So I just wanted you to know about that. So the bond that will take place between carbons there, so it is what we call what? Pi bond, I mean sigma bond. So we can bring now these all right, these hydrogens we are able to see there. Okay, now that we have this structure, I want to show you something, and we should understand how conformation happens. All right, so let's pay attention. So what will happen is that this sigma bond which we can see there between carbons, it has some characters. One of the characters is that it can rotate. All right, once involved alone, it can rotate. So the thing what I'm talking about here is, have you seen on the middle there? Let's say this bond has the property of rotating even 360 degrees. Have you seen? It can go, you move at this point, you can rotate it. So long as it is alone involved in the bond, it can rotate it like that. All right, coming to 0 degrees there. All right, so it can rotate at any angle. All right, it can rotate at any angle. So the angle will depend. So what we do, this bond will rotate like that. Okay, Okay, so once it rotates like that, we can change the directions of these hydrogens. Okay, so it's more like I can see this carbon which is here, all right, then a loop which is just the other carbon which is outside the behind the plane. All right, so let me see, let me do this. The other carbon which is behind the plane, I'll indicate it like this. So there's another carbon there, okay, which is just behind the plane. So what I'll do is I'll say there's carbon here, right, and there's also another carbon there where I've just put the dash there. So there's another carbon there, okay. So since this is another I'm just presenting the same thing, this thing that I have here. All right, so this carbon, I can see it has hydrogen there, it has also hydrogen there, it has also hydrogen there. Then also this carbon here, it has also hydrogen like that, and also hydrogen, and also hydrogen like that. Have you seen? So we'll talk more of these when we reach isomerism. So as for now, we have this carbon here, all right. So we have this carbon here and also this carbon here. So what we are going to do is, what we know, this is a sigma bond which is blue. So the property of this sigma, it will rotate like that, all right. It can rotate like goes like that, it rotates like that. So you can rotate them at n degree, all right. So this rotation, it will result into different arrangement or connectivity. So once it results into different connectivity, that's what we call conformation. So it can change. Let me say I have I have B there, okay. Let me just give an example, okay. So if I have a carbon there and a carbon there, all right, so this carbon, let's say it it has some things. Let's say I put just n hydrogen, or I present a hydrogen like that, okay, then another hydrogen there. So these dash wedges, we talked about them in the previous, it's of your choice just to differentiate the hydrogens are there. So it's not that much of worrying. Just don't pay attention to it, okay. So now I have the same compound. So here there's hydrogen and here there's hydrogen as well. So what I'm going to do is, I'm going to say I want to rotate now and change the direction of this different this hydrogen. Let's say will come, this hydrogen, you're able to see the dash, this one, and also this one of this kind. So this hydrogen, I'll change the direction, okay. So I'll rotate this one, I'll bring then this one out, it will go on the other side. So it will be, so this one is still remain the same, all right. So hydrogen is there, then this one hydrogen is still there, then this one is also fixed like that. Then I bring this rotation, this guy which will be rotating, which is the sigma bond, it has that property of rotating, all right. So what you do is, you say you bring the same carbon which you have there, then you do what, you change the direction. Now this hydrogen will go on top. They have I want to rotate it at at 90 degrees, because I mean 180 degrees, a straight thing that I'm making. This hydrogen coming to this point, it means that it's rotated 180 degrees. So I'll put hydrogen there, then these two, now this one will come at this point, all right. Then the same one, this one will just remain hanging on that position, all right. So this scenario I'm from demonstrating, or this activity, is what we call now conformation. So conformation is defined as a different position of atoms in 3D space, all right. So once you present these in different connectivity, then that's what we call conformation, all right. They will result into different orientation or just connectivity in the air or in the 3D space. So we have changed this direction, and you can see even the name will change. So this is what we call so different in positioning of these atoms from the rotation that we are from making by using this sigma bond, is what we call now conformation. Hope that is clear. So this is what we call conformation. So the rotation of what atoms result in different arrangement or positioning. Okay, so we are putting them in different position than where we found them before. So that's what we call conformation. So this is conformation of alkanes. Let's say, so this conformation we're able to see, they will result into what we call different properties. For example, if you turn into a girl, we'll call you a girl, alright? So using those characters that you are giving, we'll call you as what? We'll call you as a girl. So this guys also happens. Let's say so pay attention now. So I can let me draw the structure, something like that. This is the carbon that I'm able to see. Then this one is behind the what? Behind the plane. Alright. So that one is behind the plane. So this one is behind the plane. Then I'm able to see this carbon there. Okay. So the carbon that I'm able to see is this one, blue one. Okay, the yellow one I can't see, it's far, it's behind the plane of the one I have here. So I can put two things here. So if I put something here, let's say yellow, all right, so again I put something here, all right, so I put something red, then I also put something what, green, like that. Okay, so have you seen now what is happening? So if I put, so these are the hydrogen to say, okay, so if I put, let me label these ones as A, B, C, like that. So what I'll do is on the other side I'm going to do what, on the middle there, on the middle of these A and B is what, is a letter known as what, is a letter known as what, let's say D. Okay, D, then I have, let's say F, okay, then G. So this G, this D here, it's what is passing through between here, all right, is passing through at a point, it is bisecting A and B, all right, A and B. So this is one of the what, different in connectivity. So as a result, as it bisect at the middle there is some kind of angles there and this side, all right. So that angle probably, let's say it's 60 degrees, all right, as B, C, D, E, F. Okay, let's say this angle between A and B from D, it's 60 degrees, or even without considering 60 degrees, so long as they are not going direct, all right, they are not hitting direct, okay, they are not what, exact with the other compound on the other side. This will result, this arrangement, we call it what, staggered conformation, all right. So staggered. So if you understand this, then you won't have challenge in isomerism, all right. So this is what we call what, staggered conformation. So staggered conformation is the situation whereby the CH now, the other CH has just what, bisected the other friend on the middle between those carbons, all right. So this is what we call now staggered conformation, all right. Hope that is clear. So since this is staggered conformation, what we are going to do is we can have again a situation whereby the same D has gone straight. Let me give an example. Let me give another example. All right, so let me just lab this one. Okay, so that is what we call staggered what, conformation. So there is staggered and also we'll know the other one. So let's say I have what, C there, C there, all right. So since I have C there, then let me put a certain thing here. I put hydrogen there, all right, and also hydrogen there. So this hydrogen that I'm putting down there, okay, it will now, it will be bisecting what, it will be bisecting these two hydrogen which are down, okay, have you seen? Then also again on top there, all right, once I change the direction, it will also result in different that. So also this hydrogen is what, bisecting these two hydrogen there, it is pointing on the middle. This hydrogen, it is on the other side there, and also this one, it is on the other side of the plane. So this hydrogen is what? Bisecting these two green guys, all right, ending here if you were to make a straight line. So since they have made this, and this is what we call now staggered, so long as there is different in this group that sound to be similar, or that seems to be similar, then that is what we call what? Staggered conformation. All right. So long as they are not eclipsing, or they are not what? Making a shadow of each other, that's what we call now what? That's what we call staggered. I'm sure I've explained about staggered. Hope this is clear. Just master the way. No question will come, but you will see questions at the end. All right. So we'll see questions at the end. But in a situation whereby you are given what? When these two guys are eclipsing each other, when they are confusing each other, or when they were what? They are not bisecting each other, but they are what? Making a shadow of each other. So if I put them direct like that, let's say I put what? A and B there. Okay. So if I put what? A and B there, and also I put what? A and B there. All right. So I put again C and D there. So long as these guys are now distracting each other. Have you seen? This one is what? When you see on the other side, you can't see the other friend on the other plane. So meaning that they are what? They have made the shadow of each other. And once they have made the shadow of each other, this is what we call now what? This is what we call now what? Eclipse, because they are eclipsing each other, like eclipse. You learned about lunar eclipse, everything like that. So the eclipse will take place. So the rotation is mostly what? 360, 180, something like that. So whatever, but the different in position will result into what we call now, since they are now disturbing each other or making a shadow of each other, this is what we call now eclipse. All right, eclipsed conformation. Okay. So that's about this is how we can pray the conformation of ethane. All right. So there are two things. So we have staggered and what? And the eclipse. All right. So another example that I can give for the same eclipse. Okay. So if I have, let's say I have H there, and I have what? Or any other compound, so long as they eclipse each other. So I have, let's say, another H there. All right. So I have, let's say, CH3. All right. So then I put what? Another, let's say H, another what? H. So these things are eclipsing. This one is eclipsing that one. This one is eclipsing this one. This one is so this is what we call now eclipse, guys, eclipse conformation. All right. Okay. So this is about eclipse conformation, and also that's what we mean when you say conformation. So it's just the different positioning of these atoms as a result of rotation. Okay. So as a result of rotating, this sigma bond will form different forms. So the two forms that we can start as for now is staggered and what? And eclipse. So the other thing that I'll give you is there are things that cause this rotation. Okay. So let's say have bulk group there. Bulk group should not be the same. There's that interference. This one has a lot of electrons and also a lot of electrons. Electrons do not want to be crossed like that. They want to be independent. All right. So that's why we feel them in the orbitals. So they want to be independent. As a result, they form that tension or that strain within the compound, causing the rotation, trying to change the position of what? That distraction or interference. So that's one way this rotation can come about. It's because of this bulk group that can be crossed. So those things that cause that we call them ring string. All right, so ring strings are what are just forces that cause this rotation. So how can we know that? How can we measure the ring strain that is between the compound? So we can get a what unbranched, let's say unbranched ethane, all right, unbranched ethane, or just what any, let's say butane. Okay, so since this is unbranched butane, we can compare it, the strength that will be seeing we can put in a calorimeter or whatever calorimeter, we measure the heat, wow, it is what in what just a strain created like that, or with just a straight chain like this. So this is unbranched what unbranched alkanes. All right, so what if now I put cycloalkane, the same cycloalkane of what of butane? So what I'll do is I'll put just some point. All right, so cycloalkane there, then hydrogen there, hydrogen, hydrogen, hydrogen there. All right, so this is cycloalkane. So we'll put in a calorimeter and see the heat that will be formed, and when it is in the when we will see this, we'll measure this rotation or ring string that cause different positioning of atom themselves with a reference to sigma bond that rotate. So we'll compare these two. That's how we can know the ring string. All right, so by comparing cycloalkanes and unbranched what alkanes. Okay, so by that we'll do what we'll be able to tell, to say, okay, we can measure the heat of what we can know the heat, okay, to say this is what has happened through the use of the ring and also unlinked one. So what causes this ring string? One, it is because of the angle strain, the position of angles. All right, so say angle what strain. Okay, so angle strain is a situation whereby we have those ones on the same, let's say at the same degrees. Let's say that side is at 0, also this side. In short, they are making what shadow, and that will cause repulsions of electrons. Electrons do not want to be what's this crowded. So the other thing that we can talk with the all right, so the other thing that we can say that cause this string is what we call now, I mean this strain is what we call eclipse. So when these guys are eclipsed, they do what, they cause that rotation. You know, they once they are eclipsed, they do not want to stay while eclipsed. They would want to move further away from their initial positions. Okay, so one is when let's say hydrogen is expressed eclipsed with the other hydrogen, that do not want, like these guys, they do not want that. Okay, so the other thing is the what we can give as steric strain. So steric strain is a situation whereby atoms, when they want to, in short, atoms or groups when they approach each other, they don't want, once they are approaching each other, atoms, once they are approaching each other, then that will cause what steric strains, or just strains in particular. So they will cause what rotation, resulting into conformation, which is the different positioning of these atoms through the use of our reference bond, which is sigma bond, to rotate. So that's about these guys. So there will be steric strain, eclipse, and also angle what string. So that is the cause of what string. So now let's talk about the last thing, which is what I'll give an example of cyclo. Now let's see what is happening in cyclos. So I'll give an example of what cyclohexane. All right, so cyclo, then you put hexane, which is the hexane, just as the alkane. All right, so cyclohexane now will look like this, all right. So let's say I have what, okay, allow me, let's say I have okay, Have you seen? This is what we call what? Cycloalkane. So there are how many carbons there? So carbons, there are how many? I have 1, 2, 3, 4, 5, 6. So it's a cycle, so it has 5 carbon. So I'll put the hydrogen there. I put the hydrogen there. Okay. Then I put also the hydrogen there. So put the hydrogen there. Hydrogens. All right. Okay. So once putting the hydrogens like this, okay, so this is what we call cycloalkane. Okay, so this is how we'll be doing this. So but what I can tell you is that we'll have different arrangement of these guys. In particular, they'll be changing at this point. The way, have you seen the way they change here? So they'll be just changing at this point. This one goes up, this one goes down, just like that. Okay, so by that we can say cycloalkane, I mean cyclohexane, undergo the most I mean uh, the most what's this, stable conformation, and I'm going to tell you. So have you seen the way it is here? This guy will undergo now the conformation that I want to make for you. So what will happen is that this carbon that I have there, it will be there. All right. Okay, so this carbon that I have there, is it will be what there, and also this one I'll change, I'll bring like light like this. Have you seen? So again, the other thing that I can do is I can light like this. Okay, so I'm lighting this thing so that okay, so have you seen, I've made something like a chair. Okay, so I've made something like a, so there are how many? 1, 2, 3, 4, 5, 6. So it's still a cyclohexane. So what I'm going to do is, I've made these are just the hydrogens, so I can make the attachment there if I want. All right, so these are hydrogens. So then what I'm going to do is, I'll say this is what I've made. This is looking like a chair, right? Like a chair. So this is the most stable cyclohexane. So we are saying now the most stable cyclohexane is the what? Chair conformation. So the conformation that has just been produced is more like a chair. So we can put a kamuntu there, or a pekapeson there. All right. All right. So the capeson is resting there. All right. Okay, so this is now the most what the most, so I'll say the most stable conformation of cyclohexane is the chair conformation. All right, this is an exam question, so pay attention. Okay, the most conformation, the most stable conformation. Okay, the most stable conformation of what? Cyclo hexane is the what? Chair. The chair that we have just formed is the chair what? Conformation. All right, so it can go both conformation, half chair conformation, but just know that the most stable one is what? Chair conformation. All right, so it can be about the same thing here. I can make like this. All right, like a cupboard, something like that. A chair, just like that, half chair. But for that, just don't pay attention to such thing. Okay, let's just go there. So this is an exam question. All right, what is the most stable conformation of cyclohexane? Is the chair conformation. So hope that is clear. Okay, so these two this that what I've just formed there, it can be of two type. All right, so the two type that I can form is, there are two of them. Okay, these two guys will have also similar energy. So when you see them, don't get confused, just know that, oh, this is the chair conformation of what? Cyclohexane. So it will look like this. Okay, okay, okay. Okay. Okay, so this is the point. Okay, and also this is the point. So what we are going to do is, okay, what we are going to do is we're going to say we're going to say we're going to say we're going to bring these hydrogens like we know them. All right, so we'll put that hydrogen there, that hydrogen there, hydrogen there. All right, so I just want to show you to say whenever you see this type of conformation, you can even mask the difference. I'll show you where the difference lies on. So it's still the same conformation, which is the what, chair conformation. All right, okay, so I'm putting all the hydrogens as we can see them. Okay, so the other, this is now A. Okay, so the other one is now, our name is at B. So it's still the same, it's still the same. Now it will differ just on this point there. All right, there, that's why it will differ there. Okay, this side, this one, it will come that side there, I mean somewhere there. So what we are going to do is we'll write like this. Okay, so this will be now like this. Okay, then we'll write like that. Okay, then this one will be like this. All right, so then like that. Okay, so this one will come like that. Okay, so have you seen now the difference? The difference is that by the way, the difference is that there's hydrogen there, there's hydrogen there. All right, there's hydrogen there, there's also hydrogen there, there's also hydrogen there, and also hydrogen there. Okay, so hydrogen there, hydrogen there. Okay, then there's hydrogen there, hydrogen there, hydrogen there, hydrogen there. So the difference is only at this point in this joint. Okay, the other one, it is actually long on the top, then this one is short on the top. So the difference is on these carbons. This one, it is this side, this one, it is here. All right, so you can see the difference here. Okay, so this is the two conformation that we have. So once we change that, we bring a different, so these guys, they have what, same energy. Okay, same energy. So but if we change, let's say we change this hydrogen which is there and you put, let's say, a methyl. All right, so these guys will no longer have what, hydrogen, because the other one will be on the equatorial, or the other one will be what, on the axial position. So axial position is a situation whereby I put, let's say, a methyl there, I mean a methyl now along the x-axis, I mean the y-axis, so that's axial. So if I put, let's say, a methyl there, all right, so that is axial position. But if I put a methyl here on the horizontal, that is what we call equatorial, in the equator. All right, equatorial position. So if you see something like equatorial axial position, that's what we mean. Okay, okay, so that's x-axis, I mean y-axis is what, axial, then x-axis is what, equatorial position. All right, so don't get confused when you see this word. Okay, so that is about conformations. Hope you have what, you have enjoyed the lesson. Please guys, invite your friends, and also don't forget to share, likes our video, and also subscribe so that you can be updated whenever we post. So these videos, they are what you'll be learning in your class, so I don't see the reason of you not subscribing and also not following these free lessons. All right, okay, so thank you very much. See you in the next session.